You've probably seen this diagram before. It's from the iconic paper Attention is All You Need by Vaswani et al., which introduced the world to the transformer architecture. It's become the backbone of most modern AI models from GPT-4 to Gemini 3.5, and is widely considered one of the most significant breakthroughs in machine learning. But have you ever stopped to deep dive into it? Have you wondered why concepts like multi-head attention, positional encoding, and self-attention are so important? Or why those residual connections and feed-forward layers keep showing up? If so, watch this video until the end. We're unpacking every part of this diagram with lots of context, so you'll understand how it works and why it's important. The left side of this diagram is the encoder. Let's start with the input embeddings and positional encoding. This converts the input tokens, like words, into dense numerical vectors or embeddings, and adds positional encodings to incorporate order information into the otherwise order-agnostic transformer. Why is this important? Unlike RNNs or LSTMs, the transformer lacks a natural notion of token sequence. Positional encoding ensures the model can process sequential data, capturing relationships between tokens based on their positions. This helps the model distinguish between sentences like "the dog chased the cat" versus "the cat chased the dog." Next, we have multi-head attention. This term may sound sophisticated, but in actuality it just means learning relationships between tokens in the input sequence by quote-unquote attending to specific tokens or regions of the input across multiple heads or subspaces. But that sounds overly convoluted. What this really means is that the system looks at the input like a sequence and figures out how different words or different parts of the input are connected together. It does this in multiple ways at the same time, using multiple heads or subspaces, like looking at different angles or layers of meaning to better understand the relationships between tokens. So here's how it works. Q, or the query, represents the focus of a token. For example, if the model processes cat, the query might ask which other words are related to cat. K, or the key, represents the characteristics of tokens in the sequence. These are compared with the query to calculate the relevance. And V, or the value, contains the actual information for each token, weighted by the relevance scores derived from Q and K. Attention scores are computed via scaled dot products of Q and K, determining how much focus each token should place on others, and these scores are used to weight the values, or V, and aggregate them into meaningful outputs. The dot product matrix multiplication performed between the queries and keys results in the creation of a score matrix, and this establishes the degree of emphasis each word should place on every other word. A higher score indicates greater focus. We scale down the scores by dividing them by the square root of the dimension of the query and key vectors, and this guarantees stable gradients, as the multiplication of values leads to excessively large effects. After scaling down, we apply a softmax function to the adjusted scores in order to obtain the attention weights. This gives us probability values ranging from 0 to 1. And the reason we use softmax is because it emphasizes higher scores while diminishing lower scores, which improves the model's ability to determine which words should receive more attention. Finally, the weights derived from the softmax function are multiplied by the value vector, which results in an output vector. Only words that represent high softmax scores are preserved. And finally, we get the output of the attention mechanism. So why is this important? Multi-head attention enables the model to capture both short-term and long-term dependencies. For instance, in a sentence like "the cat sat on the mat," the word "sat" must relate to cat, but not necessarily the mat. Multiple heads allows the model to focus on different aspects of the input simultaneously, for example, syntactic structure in one head or semantic meaning in another head. Next, we have add and norm, which involves residual connection and layer normalization. These are complex terms, so let's break it down. What does residual connection do? It adds the input of the attention block back to its output. But here's why it's important. By adding the input of the attention block back to the output, it prevents information loss by allowing the original input to quote-unquote skip transformations. This is important because it ensures the original information is preserved even after multiple transformations. So it prevents the model from losing critical input information and helps gradients flow more effectively during backpropagation. Without residual connections, deep models like transformers can suffer from vanishing gradients, which slows or halts the training process. There's also layer normalization, which is the norm part of add and norm. This normalizes the output of the attention layer across features or dimensions, which stabilizes training. And this is important because it ensures that feature distributions remain consistent as they pass through the different layers, which reduces internal covariate shift and speeds up convergence during training. So together, residual connections and layer normalization makes the model more robust, which enables deep stacking of layers without any degradation of performance. The TLDR on layer normalization is that we're preventing unstable updates in parameter values, which ensures the network learns more effectively, and we're also speeding up convergence and reducing the likelihood of exploding or vanishing gradients because we are stabilizing training by normalizing the features across the dimensions. Next, we have the feed-forward network, which provides additional token-level transformations after attention. So the feed-forward network is designed to refine and enhance the representation of each token after the attention mechanism. It operates on each token independently and applies transformations that enrich the features of that token. And it's composed of two dense layers. The first layer increases the size of the representations, for example, from 512 to 2048 dimensions, which allows the network to learn more complex features. And the second layer reduces it back to the original size, which ensures that the output size is consistent with the model's architecture. There's also non-linear activation, for example, using ReLU, and it introduces non-linearity, which enables the model to learn more expressive and richer token representations. So why is this important? Attention mechanisms focus on understanding relationships between tokens. For example, which tokens are related to cat in the phrase of the cat sat. The feed-forward network complements this by focusing on each token individually, which applies transformations to extract more nuanced and higher-level features specific to that token. So the feed-forward network really boils down to independent processing. It doesn't consider other tokens because it processes each token independently, and this independence ensures that the model not only learns relationships via attention, but also enhances the quality of the individual token embeddings. For example, after attention determines that cat is related to sat, the feed-forward network enriches cat's representation to include detailed, more context-sensitive information about it. For example, grammatical or semantic attributes. The TLDR here is that the feed-forward network boosts the model's ability to understand not just the relationships between tokens, but also the inherent characteristics of each individual token. The final part of the encoder structure is stacking layers, or NX. So this repeats the multi-head attention and feed-forward network n times, usually 6 to 12 in typical implementations. And stacking layers is very important because each layer progressively builds more abstract and contextually enriched representations of the input. For example, the first layer might capture simple syntactic relationships, while deeper layers encode more nuanced or semantic meaning. In part 2 of this series, we're going to deep dive into the decoder structure, which is the right block of this diagram.